Hello, everyone. I am Ananda Krishna, a senior cybersecurity engineer with Cyberproof and organizing member of Hac'KP 2025. So, Kerala Police is proud to announce the 6th International Cybersecurity Hackathon, Hac'KP 2025. This flagship community-driven initiative brings together cybersecurity professionals, developers, researchers, law enforcement specialists, and innovators from across the globe to design cutting-edge tools and solutions that address the real-world challenges faced by law enforcement, contributing to the betterment of digital policy. Registrations for Hackathon officially commence on 25th July and will remain open until 16th August. The grand finale is set to take place from 1st to 4th October at the prestigious Taj Hotel Marine Drive, Kochi. So this year's theme, Automating the Fight Against Online Harm, focus on developing smart, scalable, and sustainable solutions to help law enforcement prevent, detect, and respond to online child sexual exploitation and abuse. We invite the brightest mind from seasoned professionals to passionate newcomers to be a part of this global mission. Registration is open at hackp.kerala.gov.in. And while there are exciting prizes for the winners, the true reward is building technology that can protect the most vulnerable in our society, our children. Now, as part of Hac'KP Tech Talks 2025 series, we are honored to host Mr. Niyas Mohammed, the founder and CEO of Neuralcraft, with over a decade of experience building AI products for enterprises and startups in sectors including healthcare, policing, and retail. He specializes in transforming cutting edge research into practical solutions for real world problems. Today, he will present Building AI Models While Blindfolded, an inspiring talk on innovation, creative problem solving, and delivering impactful results under challenging conditions. It is my utmost pleasure to invite Niyas Mohammed. Over to you, Niyas.
Thank you so much, Ananda Krishnan. Hi, everybody. Welcome to the session. I wanted to show you some of the amazing work that we've been doing at Grapnel, and I'll walk you through some of the models that we've been building and the challenges that we've encountered. Right? Couple of things that are very, very different in Grapnel is that you're working with very sensitive data, and you cannot look at the data some of the times at least. So this talk is going to be an exploration of what all we did, what are the creative things that we did, and how we overcame some of these challenges. So let's switch to the slides. A little bit about me. I've been working on AI for about the last 10 years, building AI products in a variety of domains. I'm the CEO and co-founder of Neuralcraft. But for today's session, the most important thing is that I lead the AI team at Grapnel, which means that I have a small team, about 5 people who work with me into building the AI systems at Grapnel. And one of the challenges that we have at Grapnel is image classification. There are multiple things that we work on, but today we will be focusing on just the image classification part. And so what do we do at Grapnel? Basically, Grapnel is a project that crawls the dark net and classifies information from various websites, figures out a ton of information and mines it. And part of it is analyzing whether images on the darknet are safe or unsafe. You classify them as safe or unsafe so that the police can actually go after the unsafe images. Right? So the critical part is that only authorized personnel, even within police, there are authorized personnel who can actually view those images. So, and the goal was to build a machine learning model that can automatically classify every image that we crawl into safe or unsafe. And the caveat is that my team cannot look at that data. So that was the huge challenge that we were facing. And we had a bunch of different things that we tried. And I wanted to share some of our learnings from those experiences. So the first chapter is about overcoming blindness. Now, if we can't look at the data, what do we do? So the obvious solution for us was to have the police officers who are in charge of building this model and in charge of these departments where they can actually look at the data to work with us. So the Grapnel AI team would talk to the police officers, understand what kind of images they are, because we can't look at them. We have to figure out what kind of images would it be roughly. And based on that, we would build a pipeline or a training pipeline or a code base, which I'll show you soon. And the police officers then build the model themselves. So it's very important to note that these police officers are not experts in machine learning. but they are really good experts in their field. So they're trained to detect and pursue all of these propagators of these images. So they really know their domain well, but they are not, ML engineers specifically, right? So how do we build a pipeline that helps them, that is easy to run, that is very obvious, and then how can we make it as simple as possible for them to train the models, come back with information, and help them investigate when things go wrong in the machine learning model pipeline? And once they build the model, whatever they give us, it's a job lib file, it's a binary file. We put it into production at Grapnel, and then Grapnel uses that model to predict whether the images that we crawl are safe or unsafe. So this is how the entire pipeline was structured. We had, this was kind of obvious that we had to go around this way, but the specifics are a little bit interesting. So one of the things that we did was to make it as simple as possible. So one of the first model training pipelines that we built had just 2 folders, and we built a dummy model. So we had, cat images. We literally had cat images as the safe images and dog images as the unsafe images. So we collected like 50 or 100 different images of cats, put it in one folder, 100 different images of dogs, put it in another folder, and labeled this as safe and unsafe. And what we had was a Jupyter notebook that had this training pipeline, builds all of these, runs the data, takes the data in from these folders, processes it, pre-processes it, creates the model, and then gives a cat versus dog model file. Right. And once we had that ready, it also does a bunch of other things. So there are ablation studies, and there's a lot of metrics being logged to figure out, are we doing the right things? There's a training loss curve and all sorts of things. But to keep things simple, this was largely what we did. Right. 2 folders, put in your images, run the script. It gives you this model file. And what the police officers would do is they would come and then they would just swap the images in those folders with safe and unsafe images that they had from the real training set. So we never get to see that. But the command to run the training pipeline remains the same. So what they would build was the actual model, and then we would put that into production. But it's not very easy because first, there are 2 different challenges with this. One is how do you know when things are going wrong? And second is how do we help them improve these models over time? So one of the things we had was none of this was on cloud because this was very sensitive information. So this was on police premises. They had an actual physical machine, which is a GPU machine. It was clean formatted before and after training, and only the model file was retained. So we never got access to the data. We just set up the whole VM, or the whole machine, from Linux onwards to drivers, and then you train on an actual machine, then you wipe the entire machine. So once the model was trained, how do you know it's doing well? Because the metrics that you have, like the accuracy, precision, recall, and all of those metrics will tell you that maybe the model is doing well. And it's very, very easy to get things wrong. So for example, in our training set, we had both cats and images. So the cats were the safe images and the dogs were the unsafe images, if you remember. And what happens when you get an image like this? So it will obviously say that this is unsafe. But then is that actually learning the right things? Is it looking at the dog or the cat or the flowers? How does it know that it's, how does it know, really go behind the scenes? How do we inspect if the model has actually learned something? So we gave a tool called GradCam, which kind of helps you visualize what the model learns. So the GradCam actually uses the gradients of the model to figure out which part of the image actually triggered a prediction, right? So here in our use case, if it was a safe image or an unsafe image, so if it was cat or a dog, which part of the image actually triggered the dog label heat map out? And this is very, very useful because there are cases when we had very ambiguous response. I mean, for the most part, the model was doing really well classifying safe and unsafe images. But there were also places where the police officers came to us and said, "Hey, why is this image classified as unsafe?" And we really would not have been able to explain it if we didn't have GradCam. So as soon as we ran GradCam over it and we made it part of the pipeline so they could run it themselves, it kind of drew a heat map over the bed. And then we immediately knew why, because a lot of the unsafe images that we've trained on contained beds, right, or parts of beds. So anytime it saw a bed, it automatically thought that, okay, if a bed is involved, the label should be unsafe. So based on this, we were able to go back and collect. So what we did is we collected more pictures of furniture, just pure furniture, added it to the safe class, right? So the data set became balanced over time, and we were able to train better on these. There was also another scenario where there were screenshots of file explorers where you had multiple thumbnails, and we were trying to figure out which of these thumbnails actually triggered the unsafe label. And turns out it was none of the labels. As soon as we had GradCam on, it started highlighting the grid between the thumbnails of the images, which means it was not learning anything at all. So we threw that image off. So the key takeaway here is that AI models are not black boxes anymore. You can definitely go ahead and inspect some of these outputs and figure out why your models are predicting some of these labels, and then go back, adjust your training data set, adjust your models, and then improve them over time. The training pipeline was very simple to run, but then how do you build a large data set? Because the police had a limited amount of unsafe images, right? How do you get a large data set, and how do you build a model that can kind of learn from a larger data set? So this is where Grapnel, since we were working on this for a long time, we've been working on it from 2021. We had thousands and thousands of images that we had crawled. It's just that nobody had ever sat down and labeled them yet. And the police officers are the only people who can see the sensitive images, are allowed to see the insensitive images. So basically, we can't ask them to sit and label all of them, all of the images, right? Because 99% of the images would be safe, would be considered safe technically, and 1% would be unsafe. So if we were to have 5 officers sitting and doing this labeling over time, it's a huge toll on their time, and it keeps them away from doing a lot of other things that they are tasked with every day. So one thing that we did was we took the small subset of unsafe images that they had. It was, I think it was around 50 or 100 or much lesser than that. And we also created some random images. So we took pictures of trees or trains, Ferraris, moon, Saturn, clouds, put it all under the safe images folder, and some people also. And so what it does was it creates so we took a very small architecture of a model and then trained this small architecture on the small subset of data that we had. And that actually gave us a trained model that we could use to predict over the whole unlabeled data that we had crawled from Grapnel since 2021. So we didn't take all of the data from the crawled data set. We took, like, based on the size and the variance and a lot of things, we kind of curated a subset which was still a large data set, but it was largely unlabeled. So what we did was we had the model go ahead and run predictions on top of it. Remember, this model is trained with a very limited number of data points. So you can't trust its predictions, but what we found that was that this was good enough for a start, because it was better than us sitting down and labeling all of these images. So you can't say the ones that it predicted as unsafe, you had to go ahead and manually inspect. So when we gave tools to manually inspect these images, about 80% of the time it was right, and about 20% of the time it was wrong. So we confirmed the correct predictions. We've changed the labels for the wrong predictions, and then we looked at all of the all the images that it labeled as unsafe, right? And out of which there were a couple that was actually unsafe. So anytime it was, so basically what we did was we took some small data that we had, trained a small model on it, and the small model was used to create labels for a large data set. So thousands of images, it labels, and whatever it predicted, we would manually go inspect, and then it was easy to change the labels over time. So once you changed the labels and made sure that they're all correct, now you could actually use that data set. You use that as a data set for your next model. So now you have about all of the unsafe data sets on unsafe images on one folder, all of your safe images on one folder, and then now you can actually run your training again. So This time, since we were using it on a larger data set, we had to train a much bigger model. So it was probably a few orders of magnitude. The parameters that we had was used to train a much larger model. And now that model was used to put into production. So this was one of those cases where, it's very counterintuitive as to because when people say they want to build models, they largely say that they want a huge data set. They download it from Kaggle. Some of the times you don't have label data for your use case on Kaggle. At that, in such cases, it's better that you have a small subset of data that you have, and then train a small model on it, and use that for building a larger data set, and then use that on a larger model. So you don't always need a ton of label data to get started on the data sets, on building models. So the third case that I wanted to talk about is how do you adapt machine learning models on the fly? Because model training usually happens probably like once a month or once in 2 months, because that's when you have enough data. But generally, if your model is part of a product, there are some use cases attached to it. So in this case, in Grapnel, not a lot of people are allowed, even on the Grapnel product. Not all users have access to the unsafe images. They can't view the unsafe images. There's a very specific permission that you need to have if you are authorized to view this thing. So what happens is, if by some method, right, if a model ever made a wrong prediction, right, and we don't expect it to be right all the time, right? If there's an unsafe image that contains something that was supposed to trigger the unsafe image, but the model, because it was never seen such an image before, let's say it predicts this image as being a safe image. So in such a case, what happens is, we have a mechanism where somebody, so this, if it is not an unsafe image, it gets shown to everybody, and we don't want that. So what we did is, we have a human in the loop where one of the police officers can come in and mark it as an unsafe image, right? And so that means that the prediction is corrected, and that specific image will not be shown to anyone else. So this is good for one reason, is because that specific image is never shown again. All of the all of the other users are protected from this. But there's a problem with this. If you get the same image again a second time, and if you put out any file on the internet, you know that there are multiple copies of that file online. Right? So the second time the model, so the model has, if the model has not been updated, and like I mentioned, the model training happens only once in a month or once in 2 months. A copy of the image will still be marked as safe because the model was never updated. So that's again the wrong prediction. Someone has to come back and then mark the duplicate file as unsafe again. So this was a problem because, first it is kind of duplicating efforts. How do you make sure that the same image is not labeled wrongly again? And second of all, how do you automate some of this? So there's something called hashing, where if you take the hash of a file, right, if you have an image, you can take something called the MD5 hash or SHA-256 hash. It'll give you a string. And what you can do is, whenever you're marking the image as safe or unsafe, either through the model or by a human labeler who comes and corrects the prediction, you can save this to a table, right? So you put it in a table and say that, hey, these are the unsafe images. So anytime there's a new image that comes in, before you go and predict with the ML model, make sure that you look this up on the table and see if it is unsafe or not. And if it's unsafe, basically don't run the predictions again, because we already know that it's an unsafe image. And if someone ever marked it as unsafe, you will still have the right prediction. So what that means is, any model that was ever marked unsafe through the model or through a human labeler will never be visible to the other people again, right? Because anytime there's a new image coming in, we will take the MD5 hash and then compare the table and say that this is unsafe. But the problem with the internet is, anytime you put an image online, there will be not just an exact copy of it. Sites will automatically generate thumbnails of it. There will be somebody who will open it in Photoshop or change the brightness or gradient a bit, convert it to black and white. So there are like multiple copies of these images. Whatever image that you put online, there will be multiple copies in various forms floating online. And the challenge is if you run and the MD5 on top of this, right, all of them have very, very different hashes. And not even the first characters are the same, right? Anytime you have 1 pixel difference, this whole thing changes. So that's hashing. That's the way hashing is supposed to work. And how do we go about this? So this means that anytime you have one of these images, so remember we kind of had the hash for this specific image, right? So this was an unsafe image, but then you have all of these new hashes now. And if you try to compare the hashes, then you only have the hash for one of these images in the hash table, right? Which means only one of these images, this one specifically, will be marked as unsafe. The rest of them will still be marked as safe and it'll be shown to people. Now, the whole concept is we need, if we could have the same hash for different image variants, this would solve a problem, right? And thankfully, such a solution exists. It's called perceptual hashing. And perceptual hashing means that if you have a black and white version or some sort of salt and pepper noise, some minimal noise, it can tolerate a bunch of different modifications to the images, and it'll still produce the same hash. So we used perceptual hashing. So instead of MD5 hashing, we used a perceptual hash to keep all of this information in. So anytime somebody marked a model as an image as unsafe, it goes into the table through the perceptual hash and not the MD5 hash. So to recap again, anytime we find a new model, a new image, we put it through the model either marks it as unsafe or a human labeler comes and corrects this label and marks it as unsafe. It goes into a table. And anytime we find a duplicate image or something similar, anytime we find another image, before we actually use the model to make a prediction, we compute the perceptual hash of the image and then look it up against the data table. And if it's unsafe, we just say that this is unsafe. We don't go through the model at all, right? So that is to say that you probably don't need continuous learning to keep up. There's no need for reinforcement learning, automated training pipelines to keep your product up to date. You need some way of looking at data. And by the way, so none of these methods rely us to actually look at the data. So only the police officers have access to the data. We are still out of the loop. As far as we are concerned, we just have a pipeline that computes the perceptual hash, stores it in a table. Anytime something new comes up, looks up compute the hash of the new image, look it up against the table, and then mark it as safe or unsafe. That's all we do. So we still don't have access to that data. So yes, it's so basically while you're building products, it's a lot more difficult because you have edge cases and all. How do you make sure that even if your models are not retrained, how do you make sure that the product still keeps up with all of the changes? So that's something that we did. So this is what I have for you, some of the most interesting things that we had at Grapnel. So one, again, going through all of the things that we discussed today. One is standardizing training pipelines, making sure that the pipelines can be run both by ML engineers as well as police officers. It's a one Jupyter notebook. You click around all, it takes in images from a folder and dumps the model. You use that model in production. You swap out the fake data or the toy data set from cats and dogs to safe and unsafe with the actual data, and you get a very different model. Second is we talked about inspecting images with GradCam, which helps you inspect which part of the image actually triggered certain labels. Third is automating labels with smaller models. You take a small data set, use it to train a small model, use the small model to make a prediction on a larger data set, and then use that larger data set to train a larger model. And the last one is perceptual hashing for detecting similar images. So instead of MD5, how do you make sure that you detect similar images through the same hashes? Right. So this is what we have for you at as part of the ML team, the AI team. We've been building a lot of things on not just images but also text. But that's a topic for another talk. And if you're interested in any of this and you want to join the fight against all of the bad stuff on the internet, join us at the Grapnel team. We would love to have you as part of the AI team. And connect with me here, and I'll be happy to chat and then figure out what we can do. So that's it from me, and Anandu, back to you for questions.
Yeah, that was a wonderful session, Niyas, and I think we all walked away with much clear understanding of building AI models and how these concepts can be applied to solve real-world challenges. And this insight shared today had given us practical ideas as well as inspiration for the work ahead. Now, before we close, I would like to take a moment to hear from our online audience as well. We had some excellent questions, I believe, coming in through the live chat. I want to make sure we address at least a few of them while we still have the chance.
Sure. Awesome. So the question that we have is, what metric was optimized when we are training the models? That's a really good question. So a lot of data sets are balanced, which means that you have half of the data is, cats or dogs or whatever, right? But here in this one specific use case, we had the rarity of labels, right? The unsafe images was very, very few compared to the safe images. So the metric that we used was recall. We optimized for recall, and recall was basically what recall says is it's okay if you err on the side of caution, and if it's okay if you classify a few safe images as unsafe also, right? But basically never say that an unsafe image is a safe image, right? So basically that's what we did. We optimized for recall at 1, and that's how the models were trained. Super good question.
All right. We have another question.
Awesome. So
Yeah.
the question is, what architecture models are used in training for Grapnel? So we have a lot of different things happening at Grapnel, including transformers and LLMs. But for the things that we were talking about in the image pipeline, so the smaller model was, I think, a ResNet 18 model, and the bigger one was the model that we trained finally for production was a connext model, if I'm not wrong, connext or resnext, one of those images. It had like a ton more parameters than the ResNet 18 model. Awesome. Good. Someone is asking how I can join the Cyberdome. Then you can probably talk to some of the folks here after this workshop and then get to know this.
All right. For the online peeps, if you have any more questions, feel free to ping on the comment section. Okay, there we go.
Oh, a lot of questions on where it was hosted. So the model was hosted, in a private instance. So all of the infrastructure that we had was on a private network, and it was hosted on a GPU machine for the image processing because we had a ton of images coming in, and it was basically a batch process. It was sweeping in, making predictions, and then putting it out, right? So that was what we used for the image processing part. But there was also lots of models that we had that were running on Kubernetes jobs, right? So basically, it's like a very small, like a 1 GB RAM, like a cube job, and all those models were running locally. That's for text, but for images, we had a GPU machine that was within the Grapnel infrastructure premises. Awesome.
I guess there is a question about the architecture models also. Do you,
So
do you
the
want to?
architecture. So again, so this architecture was. I think we addressed this for the image models. For text, we have a lot of other things. So text. So this is about the text. So since we talked about text, maybe talked about the images. The text models were a lot simpler. We had very, very basic transformer models, and we were using a lot of things like regex for matching phone numbers and email addresses, which is like still the fastest way. You don't need an LLM for everything. So a lot of those things that are running locally using very cheap stuff, they do the first phase, and then for more complex things like images and all, we use like a connex model, or more recently we're also expanding with LVMs, which is large vision models, right? How can you and also things like clip models, where so you have an embedding of an image, and the embedding, so the image embedding can also answer questions. So you create an embedding of an image, and then you can query for houses, blue houses, and then it brings back images of blue houses, because it can combine both text and images into the embedding, right? So quite a lot of things that we do here. Did you try any quantization techniques for deploying the models? For this one, no, we didn't, because it's not huge. It's like a few megabytes, but then we did not want to sacrifice any of the performance for the models that we have now. For LVMs and all, yes, we are experimenting. It's not in production yet, but definitely we would need quantization, right? So the trade-off is like, how do you trade off performance for the size and volume? And also, how do you make sure that it is very fast to compute? The time to first byte, or time for the first token, time to first token is very, very quick, right? So it depends on the use case. We are experimenting with LVMs, and then that's where all of the quantization would come in. Oh yeah. So how often do you train the model? Specifically in this scenario, the pictures are from darknet. That's true. So the models are trained once or twice in a month on a regular basis, and when the product is live. So a couple of things that we do when training the model is, we can't take a random sample of the images from whatever we have. So what we do is we kind of make sure that it's a wide array of images, right? So there's a technique where you can sample images based on the distribution. So it can be a group of people, it could be isolated people with blank backgrounds and all. So it's important to figure out what is the data distribution. So even if you don't look at the actual data, you can look at a cluster of the embeddings that are plotted, and then figure out what's a rough sample. That's a good sample that you can take for your training. The second thing is, we also need to correct all of the mistakes that we made in the previous version of the model, right? So anybody who comes and relabels the model, right, in the use case that I showed, if the model is wrong, somebody comes and corrects this, you need that to be there in the model training set from the next time onwards, right? So we also take that into consideration when we retrain the model. Okay, what can go wrong if we build AI without enough data or understanding? How can we stop it? So there's a lot of things that can go wrong if you build AI without enough insight into the data. So one of the classic examples that I can give is Amazon, or one of the biggest big players. I think it's Amazon. They built a model that was used to detect criminals, right? So it was trained on a lot of criminal images, and then they put it into production, then gave an API out, right? And somebody just for fun tried to classify the people in the US Senate as criminals or not. Like, I think about 50% of them were classified as criminals, right? So so if you don't actually so there was another case where when Google Photos came, right, on your Android phone, you could take pictures and then search by text within your camera roll, right? So if you search for tree or house, it'll kind of classify the images that you have in your gallery as trees or house. Right? For some reason, somebody searched for gorilla, right? Probably because they've taken a picture of gorilla, but actually it brought up pictures of Black Americans, right? And Africans. So such things can happen, and it can not just be, it not just be bane to your name and quality, but also things like in healthcare. If you're wrong, if you train with the wrong data or bad data, then the implications are like, it be somebody's life would be in peril, right? Somebody will not get insurance, somebody will not get treated properly. So it's very, very important that you investigate. There are a couple of ways that you can do this. One is through explainable AI. You actually look at your predictions, right? And the other one is while you're creating the training set, make sure that you have a good representation of all of the things that you expect in your data set, right? So if you're creating some sort of a classifier for Indian people, make sure that there are Indians in your training set. Don't train it with all the Western people and then put it on the Indian data set, Indian audience for production. So yeah, those are some of the things that you can do. So Ardra asks, how can missing domain knowledge, poor quality, and weak validation process impact a model accuracy and reliability? So, so this is one place I think the AI team has to work in close connection with the domain experts. Right? In this case, my team is specializes in building AI models, right? But we don't necessarily have the full domain knowledge, as in we don't know what happens, what is the workflow, why does this image get detected? I mean, what happens when somebody flags this as an unsafe image? What does the police do, and do they need a report, right? Do they need to figure out where this image first originated, right? So if you don't have an understanding of what you're building for, right, not just the model, but then what happens afterwards, then it becomes problematic down the line. So if you know this early and you can understand what is the purpose of this model and what happens afterwards, and then do people act on it? Is there a department that handles this? Right? All of those things are important, and it's important that the technical team, the AI team, knows and learns about them so that they can have the right workflow and architecture for deploying these models. Sometimes it can be like as simple as, a change between, you can save hundreds of thousands of dollars if you run a batch process. So even today, if you run OpenAI, right, if you use the API in real time, and if you use it as a batch process, which means you run it only once a day, sometimes you schedule it and then run it, right? The batch cost is like half of what you would pay for if you were running it in real time, right? So there are things like that. You can save money, time, a lot of impact also, if you just make sure that you have the domain knowledge, and you understand when this is run, why it is run, and what is the impact after you run this. Oh, yes. So there's another question about, are there any biases in the training data that the model might be exploiting? See, that's what, so remember the example that I showed regarding the bed in the image, right? So a lot of unsafe images contained a bed. It also contained people. So anytime the model saw a bed, it started automatically classifying the image as unsafe, right? And that's called a bias. So it's not conceptually understanding why the image is unsafe. It's just saying that, hey, if there's a bed, then I should mark it as unsafe, which is the wrong thing, right? So this can manifest in very different ways, right? There were certain data sets in Kaggle, which is about classifying fish, right? And the data set contains images that are taken from a ship. So you have part of a ship and the fish on top of it, right? So on the board of the ship, you have the fish. So that's the picture. So a lot of the machine learning models that people built scored very well on their the public data set, but on the private data set, which they actually score you on, they scored very low. And the reason was that a lot of these models did not look at the fish. They actually look at the board and figured out what was the ship. And that ship was in the Indian Ocean at this portion. So probably it was always capturing this particular thing. So even if your metrics are like really high, right? You score 99% accuracy or recall or F1, your model still might be learning the wrong things. And it's very important that you look into why these things are why these models are predicting these labels. And that's where things like GradCam or SHAP or Line can help you explain your model predictions. Awesome. So I guess that's it, Andu. Yeah, I guess those are all the questions that I can take on. Back to you, Anandu.
All right. Sorry, I just got disconnected. So I see a lot of questions regarding how to join the Cyberdome. So guys, if you're interested in joining the Cyberdome, just visit the Cyberdome website. You will get more details. And or else if you can just put up email drop at cyberdome.pol@kerala.gov.in. Right. So thank you so much, Niyas, for this truly insightful and inspiring session. I think we all can agree that it gives a fresh perspective on how the innovation and creativity can thrive and even under challenging circumstances. To everyone who joined us today, thank you for your time, your engagement, and for being a part of Hac'KP 2025 Tech Talk series. Remember, the hackathon is already live and we are counting down to grand finale from 1st to 4th October at Taj Hotel, Kochi. If you haven't registered yet, just visit the hackp.kerala.gov.in and be a part of this mission to make the online world safer for children everywhere. On behalf of Kerala Police Cyberdome, we wish you all the best, whether you're competing, collaborating, or just here to learn and share. Stay curious, stay inspired, and together, let's keep pushing the boundaries of what's possible. Thank you, and see you all at the next Tech Talk.